Hello everyone. You all successfully attended this meeting, and I hope there will be no technical problems today. Yesterday we did have a really successful meeting, and I hope all the presentations were interesting for the audience. We were dealing with masonry structures more or less. And today we will have several presentations about timber engineering and assessment of existing timber structures. So I know the audience is a little bit different. So I will just shortly repeat the presentation from yesterday about the ARES project. I will try to do it really fast, so to not repeat everything I said yesterday. And then after this we have several presentations. I will introduce all of the presenters, and then we will have a discussion if somebody will have questions. Okay, so let's start. ARES project is ARES stands for Assessment and Rehabilitation of Existing Structures. It's a Croatian Science Foundation project with a duration of 5 years. We have several working groups from masonry, timber, reliability, and experimental work, and structural health monitoring. The working group is divided like this: principal investigator, that's me, and 2 PhD students, Luka Lulic and Karlo Ožić. Luka is working for 8 months now, and Karlo just started last week. We have several working groups, as I said: masonry with 2 PhD students, Tvrtko and Ivan, timber, Jure and Nikola, and reliability with a full action member, assistant professor Robert Jockwer from Chalmers University, and then we have this experimental work package with structural health monitoring with PhD student Janko Koščak. Also, to implement our work successfully, we have several advisors. From masonry, there are Chiara Bedon from University of Trieste, assistant professor Chiara Bedon from Trieste, Professor Tomislav Kišiček from University of Zagreb. For timber, it's Professor Vlatka Rajčić from University of Zagreb. And then we have in reliability, we have Professor Gerhard Fink from University of Aalto in Finland. And unfortunately, Daniel Honfi is not working anymore at ARES, so he will not be the part of the working group because he has some other obligations now. And then we have, of course, for experimental work, all of the professors from University of Zagreb with Ivan Dubnjak, Domagoj Damjanović, Marko Bartolac from our lab, and of course Professor Kišiček, Rajčić, and Chiara from Trieste as advisors. So I will not go to these objectives because I was talking about them yesterday. So I'll try to shorten this presentation, but the presentation will be online so everybody can see what are we basically doing and what are we dealing with this in this project. And this is a timetable or timesheet of the project. So we decided to have 20 different case studies, 10 for timber, 10 for masonry, and we will do proper assessment, on-site assessment, proper modeling in the office, and we will have several case studies also with proper structural health monitoring and continuous structural health monitoring. In the end, we will do some reliability and proportionality analysis just to achieve material properties, loading history, and parameters that are influencing structural performance of buildings. In the end, we want to produce something to engineers to help them in their normal daily work. So we have several project modules. First one is development of concise database of structures and assessment techniques with compilation of inventory and of inventory of material properties and load types. Then we have model development, analysis, and sensitivity studies in module 2. In module 3, we have model verification and optimization with some experimental work in the lab. And in the end, we have evaluation of proportionality and reliability and design and development of design guidance. So in the end, we want to produce something to help all of the engineers in the field to have easier and quicker assessment of, and of course, more correct assessment of existing masonry or timber structures. As you probably know, Zagreb was struck by an earthquake in March, on 22nd of March. So as this project started on 9th of January, before the earthquake, and we are dealing with masonry and timber. So for us, this is actually the great opportunity to have a lot of case studies, because we will have opportunity to assess more buildings because of this earthquake. So you can see on the left, on the figure on the left, how one normal street in the downtown of Zagreb looked like now after the earthquake. Earthquake was moderate to severe, so we don't have a lot of collapsed buildings, but we have a lot of damaged buildings. So basically, next 5, probably 10 years, we will do the rehabilitation and renovation of this kind of buildings. And these kind of buildings are of course masonry buildings with timber roofs and timber floors. On the left, you can see also some structural heritage objects which were heavily damaged. So today we will have several presentations. So it will be several of us from University of Zagreb. Then we have Robert from Chalmers University in Sweden, in Gothenburg. Yesterday there were some presentations from University of Minho. So if somebody is interested, they will be also put online on our webpage. Chiara will have one presentation. Chiara is coming from University of Trieste. Then Igor and Istok from INORINU and University of Primorska, from Koper from Slovenia. They will share their knowledge from the assessment of existing structures in Slovenia. And I'm particularly happy because we have 2 designers who will share their knowledge. So it's David Andžić from Studio Arhing and Ivan Maturić from People's Associates Structural Engineers, who I'm really thankful to share their time, because it's not very often that people want to produce and to show and share their knowledge, because they are always too busy. I must say that Ivan and David are very interested in this work package. We are doing it with both masonry and timber, and we'll see what they are doing in their professional time. I also want to share how this project started. My background is in timber engineering. I finished my PhD in timber with my supervisor, Professor Rajčić, and this is one of the papers we published when I was working at the chair of timber structures, both with Professor Rajčić and Jure. So the title was Inspection and Condition Assessment of the Existing Structure. So it's basically state-of-the-art paper about assessment and condition assessment of timber, with some techniques and NDT, both NDT and DT methods, how to do it. Then Professor Rajčić will have some advanced, she will have a presentation about advanced methods and how to assess both heritage and how to digitalize these heritage buildings, mainly in timber. She will have it after my introduction. Later on in this year, we published with Igor and Istok this kind of paper in the MDPI journal Applied Sciences about seismic design of timber buildings, where we also have one small part about problems in assessment of the buildings. After that, we published one paper with our group from concrete and masonry chair, and together with Chiara, about methods for assessment of critical properties in masonry structures. And basically we just talked about also with some objectives of ARES project dealing with masonry. I also published one paper with my colleague Matteo from Faculty of Geodesy about new technologies. So we try to stress out why are we not using also new technologies such as photogrammetry, drones, spectrography, and other methods. So if anyone is interested, it's free of charge. This paper is open access and you can download it very easily. And last week we published one paper also about strengthening of masonry with FRP and TRM. It's also open access, so you can download it. And then I just want to show what we done yesterday. So yesterday we have several presentations about masonry engineering, and today we will have several presentations about assessment of timber structures. First, after me, there will be our group from chair for timber structures, and with Robert, we will have a short online coffee break, and then we have several more presentations, and in the end, discussion and ending of a meeting. So basically, that's all from my side. And now I want to introduce Professor Vlatko Rajčić.
Good morning, everybody. My presentation will be connected with the Horizon project Inception. The work that we done in very important task, which is very important for the cultural heritage. It is digitization and 3D modeling of the cultural heritage. And available, this is a very large data that will be after all this digitization made in the world. So what to do with the data and how to manage the data. Inception was a very, very complex project with lots of topics, and I will try to explain the main concept of the Inception project, main goals and some of the results we have achieved. You see it's inclusive and time dynamic 3D reconstruction, it's aim. So for everybody from everywhere, so it's inclusive for everybody, for all types of professions, and in somehow model that everybody can use it. So as you can see, it's from the program of Horizon 2020 Reflective, so it's social programs, and this is this concept that try to bring cultural heritage to everybody. That can be used from remotely to visit cultural heritage sites. It started in 2015 and ended at the end of 2019. You see the web page if somebody interesting after that, so there is a lot of materials. I will bring just a very, very small amount of the information. In this 15-minute strategy, it was to create inclusive understanding of European cultural identity, extending knowledge of cultural heritage, improving the accessibility, which is now not very good, and stimulating collaboration across the disciplines and technology sectors related to cultural heritage. Also, objectives were innovation in 3D modeling, and including time dynamic reconstruction, so that we can see the object through the whole period of exploitation, all the reconstructions, all the things that were done during the time into the object, and implementation of innovative protocols, how to collect the data, acquisition of the data, and how to capture. That was the work package 1. So consortium was from the 40 partners. You see 10 European countries and 5 university, 2 research centers, 6 SMEs, 1 industry, very important because they are producing a laser scanner. And in this project, they developed software as well as hardware just dedicated for laser scanning of cultural heritage object. This is our team. From UNIZAG, it was mainly a chair for timber structure. Misla was there then in that period with the Jelena Blajcifer, which is not from the timber structure, but she helped us with the BIM. This was some aims, and we will now go to what we done, University of Zagreb. You can see one of the case study. We have had 2 case study. This is one of this one Technical Museum, Nikola Tesla in Zagreb. And for the capturing of 3D data, we use photogrammetry and as well unmanned aerial vehicle drones. And this is the models that we obtain by drones. What we used is, this is our equipment. It's, as you can see, Cadmic Goliath 8 Max system that is consisting of drone with payload up to 5 kilo with 8 propellers. This is some technical data and could be navigated via GPS, could be manually navigated, and what is very important, it has all the displays on the land, on the tripod, and you can see everything that is going on with the drone on the monitor. The flight can be also navigated manually by GPS assisted or safety mode. Time flight is maximum 30 minutes, but in practice it's better to stay 20 minutes in the air. We had also one smaller drones that we used. You can see it is possible to put several devices on the gable of this drone. We usually combine a camera and a thermal camera to see what's in the roof and all around the structure. Further on, we done with the help of University of Ferrara laser scanning of Technical Museum, obtaining point cloud of very high accuracy. So now museum have every points in a very, very accurate manner by this laser scanning. Having these 3 data and lots of data from previous period when we done reconstruction works and assessment and NDT testings and all kinds of visual inspection measurements, which will be presented by Jure after me, we were ready to put this case study on the Inception platform. This is the Web Inception platform, and this is the main result of the project. I will explain step by step. It was developed during the project. It was really brainstorming how to do it. It was lasted really through the whole duration of the project, and finally we got to this scheme and to this kind of management and using of this data. So after capturing this 3 data for Technical Museum, the next step was to make a BIM model of the Technical Museum. The building is cultural property, a rare existing example of European engineering concept. For expo halls, there was lots of expo halls, not many of them still existing. So for these expo halls, dimensions are 85 meter on 40 meters, and it is built in early 20th century, but this kind of structures were mainly at the end of 19 all around the Europe. Our focus was on modeling timber structure of the main hall, that is hall A. You see it, structure, and covered the whole object. BIM model was modeled in Revit software and was reconstructed from the available documents and on-site measurements that we done before. Layout is, as you could see, a curved plan, a cutoff of curved plan, and the BIM elements are structural and non-structural. So regarding the structure, we have trusses. We can have primary and secondary trusses. Longitudinal in longitudinal way, it's secondary trusses. You can see it above. all the trusses and all the elements were modeled parametric as parametric families. So if you change one thing, you don't have to change all the elements. Everything is changed according to the only changing one parameter. So we had a lot of beam systems, for instance, on this gallery, also on the roof, and there was a very large variety in forming the columns, which are multi-part columns with the diagonals. Diagonals are space diagonals forming such a very high bearing capacity columns. With also bracing systems, of course, in the structure. And non-structural elements were, we can see it here, curtain walls, floors, and the wall finishes. So we now see impressive structure, which is not could not be seen when you enter the museum because it's all covered with a lining. We will see the picture. So we try to emphasize that it is a very valuable structure underneath of this layup of technical museum. As it is very complex structure with also, as mentioned, curved lining plan, there was a large number of elements. There was a very large files, heavy files, which had to be uploaded into the beam server. So this is the scheme, a little bit just upper part, because we are coming from three parts as input survey data, then from the beam model, and on the right side semantic, which is very important. I will explain later. So this inception platform on the left, survey data, we also put metadata or paradata or any other layers into the beam server, and this central part is a beam server. That means that the beam model from IFS standard, whatever software you are using, you get IFS standard format. And here you can also put additional graphics info as an input to the beam server. Usually we, for the additional graphic info, use some graphic files, and especially for another object, it was a texture of stone. But for this, we didn't so much put trouble into the texture of certain layups. This is the beam server. So the data are coming to this beam server, and it is the interface where we prepare the model to the conversion. So in this part, you can also add some properties. You see that it is everything is semantically arranged, and you can see the elements as doors, slabs, stairs, and so on. But also you can select them by the dimensions and some other characteristics. Further on, there is a possible on the right side path for input semantic enrichment. For the inception platform, semantic data store is chosen, not object-oriented programming, but the semantic. And for that, powerful Sparkle 1.1 support engine was used. And the same engine performed powerful queries inside specific 3D IFC model also. Different options can be used as well, as it is one unique solution. And also with this only semantic data, we can visualize the Sparkle query results. We will see it later directly in the web-based 3D viewer. So we are actually going from the beam to this another type of format. So from IFS to RDF format. IFS is well studied. It's this BIM format. Also, it's freezing and documenting the design status of model. And this is for this platform. It is very good that you can model in all kinds of software. So it can process the data irrelevantly which authoring platform of IFS you used. So IFS, so this BIM models, is now transferring in so-called resource description framework. It's a family of World Wide Web Consortium specification. So format originally designed as a metadata model, and now it is established as a general model for conceptual description of modeling of information that is implemented in the web resources. And it is also adopted as a World Wide Web Consortium, and it is recommended already in 1999. Also inside, also partners were, of course, ICT companies which done that. There was a routines for the extract semantics from IFS files. The Inception platform is based on Fuseki solution, Fuseki 2 solution. Although it was normally say Fuseki 2, it's actually, as you can see, Apache Siena Fuseki, and it acts like Sparkle server. This version used by Inception platform has support for Sparkle 1.1, which is relatively new and has a really very powerful features. It is free open source level framework for building semantic web and linked data applications. It can run on different operating systems. Inside the Inception, for instance, we use the Windows-based system, but you can use it on the Linux, Mac operating system machines, but also on the Android, smartphones, i operating system like iPad, and so on. Regarding the Siena library, of Fuseki 2 solution, it is able to apply inferencing of the data. That is very important. It's highly configurable concerning the inferencing rules, and it allows different inferencing engines to plug in. This means that we could choose the best inferencing engine for our problems, and this one, which was established in Inception project, could be improved further and have maybe faster performance and better performance. So it is available for changing and configuration on your specific problem. So after that, we are now in RDF format, and that format we can also do the visualizing of everything that we need. This is one case study from Spain, a very old fortress. Also, elements of the model on the web platform can be selected by the semantic. So indeed, this RDF format, everything is done and chosen through the semantic characterization. So on the right, you have this all the data of selected elements of the elements in the form of semantic data. So if you choose, for instance, you can choose selection by the thickness, by the material, by the age of some elements, and so on. Also, the whole files can be treated as semantic documents. Coordinates or GPS system already brings you one semantic level, so the position where your object is and after that we have this using of Inception platform, and one option is time machine, which this project is famous of. So you can put also the time dimension in your modeling, For instance, we done it with our case study, another case study inside the Technical Museum, which is not so new. It's from the 1948. But this other case study was a very old church in Dalmatian Zagora. So we built this model as a history model through 4 phases. You see, from 1688 until 1911, it has 4 phases that we could find in archive. And it is mainly always addition, of course, to the existing one. So on the Inception platform, we can see this available time, so-called time machine, time dimension, look at some object so you can see it through the time. Also, another possibility of use through the Inception platform is versioning. So we can use this data for all kinds of purpose. For instance, in the Technical Museum, we done this application for the artifacts in the Technical Museum. So in Tesla, for instance, cabinet, we done it for the all artifacts. So when you put your, it's based on the one you can see on this automobile. On the shape, you just put your application tool and find the shape, and when it suits to the shape, then you get all the information about from the all kind of data that you retrieved before about artifacts, so you can see what you put. You have all the photographs and technical information and so on, whatever you want to show to the visitors. Also, we can make all kind of virtual tools. We can make films. We can buy the augmentative reality applications, so virtual, all kind of tools. We can go through the object, through the virtual reality, all kind of applications. So if I have a time, I don't know if I have a time.
You can do it. Yeah, we have time.
But there is one additional thing that I was planning to show you, which is not here, but it is connected to the application. There is on the Inception website, you can see a lot of application also for the Technical Museum, when you can put also application and see beneath these linings, you can see the structure. For the visitors, they can see beneath the real museum, they can see the whole structure. So if you are interested, you can go to the Inception website, which was presented here, and you have a YouTube's also for 3D and time machine. Especially well was established and refined one case study. That's the Innocenze Center in Florence, which is going through the times. They have lots of phases in which they develop their model. So that's all. Thank you very much for your attention. And if there is some question, I don't know if they will ask now or later on.
Thank you, Professor Rajčić. I can add, I will produce one PDF with all the CVs, so I can also add some additional data with the links to
yeah, there's a lot of links and you can visit it. There is really lots of animation and you can see very interesting things. And you can use the platform. So it's only with IFC, you can also bring your object into the Web Inception platform. So I suggest if somebody is doing BIM and have BIM model that can check out how the Inception Web platform functions.
I was really happy that I was also one part of this project, and I encourage everybody to see what we were doing in this project, because I think this is future, especially for heritage types of buildings. So I will put some additional data on the PDF I will produce, so everybody can see what we have done, especially what we from Zagreb have done with the lead of Professor Rajčić. So thank you for. Jure, are you here?
Yeah, do you hear me?
Yes.
Okay. I will talk something about condition assessment and retrofitting of the Nikola Tesla Technical Museum in Zagreb. So this project has been going on for a long time, and the entire team from the chair for timber structure participate in it. So in short, I will try to present you what has been happening for the past now 11 years. So at the beginning of the 1948, architect Marian Haverle designed a temporary building for the needs of the fair. Today, this place is in the wider city center, but in that time it was a place of the tram depot. So the city government decided to remove the depot and make the new representative building. So the construction was led by the company of Viskogradnja, with for that time and valuable coordination of the work and the construction site and the workshops along it. So it should be noted that all construction was done with hand tool and cranes, without the use of the now modern machines. So with the relocation of the fair in the period of the 59 to the 63, the building finally housed the technical museum. So in 2009, for the first time, condition assessment and serious retrofitting work on now protected cultural heritage buildings were started. So we can say that the whole complex can be divided into 4 buildings. The main museum building, Hall A, which is the timber construction. Hall B with offices, workshops, and storages. That part is partially concrete, partially masonry, and smaller auxiliary buildings, Hall C and Hall D in the yard. Due to the complexity of the structure, on the model you can see that there is more than 10,000 elements made of the 2,080 cubic meters of the lumber. So the detailed steps required for assessment and planning of the intervention. On this chart, we can mark the central part as the most important, due to the fact that the works were carried out in the parallel with the work of the museum. So there was a need for a good coordination. We started with the overview of documentation and visual survey. We also made the plans on which you can see the longitudinal and transfer cross-section, as well as the roof construction and the base floor plans. So the building is formed in the segment of the circle, with the central main hall and the lateral lower parts. So after that, we made some non-destructive tests, wood moisture, as well as the measurements of the ambient humidity and the temperature was done. On the sketch, you can see that the construction is very well dry condition, with some exceptions on the roof, where the wood moisture content rise up to the 20%. The main reason was the point cracked or damaged roof insulation. But the problems occur due to the drainage, which help water retention of the mostly east courtyard side. It results with the complete rotten basis of the columns. What was the biggest problem in this retrofitting jobs. We also made some ultrasonic determination of the modulus of elasticity, and with some resistograph inspection on the some cracked or damaged elements. We also start with the after we made some preliminary tests and examinations, we start with the main roof trusses inspection. So on the picture you can see how large it is. Also on the right side you can see the brace system of the upper and lower cord, as well as the longitudinal vertical bracing system. During this inspection, we most often found the problem of cracked elements, which we solve with the filling with the epoxy glue if there was a small cracks, or we use the steel clamps if that cracks were bigger. Also we found some problems on the tensile extension joints, as well as on the step joints. So again, we use additional steel elements and epoxy glue as the solution. But the bigger problem was the insufficient number of the fasteners in the joints, as well as the torsional damages of some elements. So on this side roof trusses, we can see how we solve that problem. We use additional new elements just up to the old one, with sufficient number of the fasteners, or better solve the joints. After we examined the roof trusses, the next problem was the gallery floor beams, because there was a seriously torsional damaged. On the next picture, on this end, you can see how twisted they are on their ends. We just put some steel brackets again on the beam ends to prevent torsional effects. Also, we found some cracks which we filled with the epoxy glue. Next thing, which was our biggest confront, was the rot of the columns. We found the biggest percentage of the rot in the eastern and western facade columns. So the solution was to hold the whole structure above the columns, cut the bottom, and put some new steel elements to solve this problem. Of course, we put additional steel brackets on the top of the columns to connect columns with the horizontal beams and trusses. Also, when we examined the northern and southern facade columns, there wasn't such a big problem, because we found just smaller cracks and partially problem of the joints in the bottom of the column, but it was easily solved. The bigger problem was the inside columns, because there was again a high percentage of the rot. So we put the additional base made of the concrete. Again, we hold down the structure above the column, cut the bottom, and put this concrete base with additional steel elements. And again, the standard solution for the cracks was the epoxy filler. So after we solved the problems with the whole construction elements in the roof and in the columns, we started to examine the stability of the whole construction. So in the original, only bracing on the gable sides was done. of course, in the course of the timber elements. But then we decide to put additional transfer bracing system. The green and the yellow, the new one. So we put the steel braces in the facade part in the middle. Middle part, and also on the we put the bracing between the bigger columns on the end and the middle field inside the building. So this solution was very good and easily to control during the time. So our final job was facade inspection and renovation. Although mostly architects designed this facade, we also made some job about design the connectors of new facade, and as well as the inspection of the facade construction. So the interesting thing during the inspection with thermography camera was that you can see through the wood paneling the main construction or timber trusses inside of the building. So it was very interesting to present this type of the inspection. So that the assessment work is permanent job. We were able to convince during the earthquake in the March this year. So our main target during the inspection was the condition of bracing system, as well as the condition of the joints in the columns bases, and again, of course, the roof trusses. We found that the most of the joints in the base, column bases, and the bracing, the diagonals are in the good condition without any damages. In the roof trusses, we found just a few damages extend up regarding appropriate type of the fastener, as you can see on the picture, but there wasn't some serious damages in the whole construction. After that, we made some preliminary numerical modeling of the construction part, and we put the highest ground acceleration for this type of the state, and found that construction is okay, but the displacements on the rooftop was something bigger than the limit one. So we conclude that this bracing system, the new one, the steel bracing system, should be extended up to the roof truss. What was I can say what was a logical solution. And after we put this bracing system in the model, this displacement on the top was in the inside of the limit. So for the end, we hope that this 70-year-old temporary building will experience at least its 100th birthday, and that we will in the future have more opportunity to explore its maybe a little bit dark but interesting construction. So it's everything from me.
Okay, thank you very much. I think we will go further on because we are 10 minutes late.
Yeah.
So Nikola, are you ready?
Do you hear me yet?
Yes.
Okay, great. So I'm ready. Let me just share my screen, please. So are you able to see it? Yeah. Do you see my screen? Yeah.
Yes, we see it.
We see.
Okay, thank you very much. So, hello everyone. First of all, I hope you are all very well in these chaotic times. I'm very sorry that we cannot see each other and let me say socialize normally, but it is how it is. We'll all have to be a little more patient. I believe each of us can't wait for all of this to end. Of course, I don't mean this workshop, but the epidemic situation. I have to joke a bit. I hope Mislav doesn't mind, considering how strict and serious he is. Anyway, I would like to thank Mislav for inviting me to this workshop and give him a credit for all this great work done. My name is Nikola Perković, and I'm research and teaching assistant at the Faculty of Civil Engineering at the chair of Timber Structures. In this short presentation, I would like to show you the problems we encounter when expecting wooden roofs, as well as possible solutions. All of this can be seen in the case study that characterizes the typical type of structures in the center of Zagreb. So, as you may have already seen, you can find a bit more information about me here, as well as an abstract, but I wouldn't dwell too much on that because Mislav has already introduced us several times. By the time I should have finished it already, so I'll do my best to convey to you what I want in the shortest possible time. I won't forget anything important to say, hopefully, but please feel free to interrupt me and ask me a question. Given the limited time, I would just like to briefly introduce you to the content of today's presentation, all in order to make it easier to follow and systemize it. So you can see in this current slide the content. So let me start. So I'll start with brief introductions. So let me say a few words about timber and wood. So for centuries, wood has been used as a structural material. However, timber structures can experience significant deterioration and damage, limitation of use, and are often require replacement or retrofitting. It is therefore fundamental to define methodologies to assess safety and to predict how safety will evolve the time. In the case of typical roof systems, stresses and deformation can be calculated considering linear elastic analysis based on finite element analysis or the displacement method. Due to simple nature of the most timber structures. Complexity, on the other side, is increased by the influence of flow duration and moisture content. Also, the geometry, of course, the geometry of the cross sections is an important parameter since members with irregular cross sections are large variability along their length may be found, especially for older structures requiring time-consuming in situ measurements. The first theme I would like to comment is standard and guidelines. So over the past years, a multitude of guidelines on how to approach the inspection and maintenance of existing timber structures have been published. However, only a few countries have published, let me say, applicable code type documents for the assessments of existing structures. Having said that, there is a large number of methods and guidelines for the assessment of existing timber structures, but some of them are applicable only for a certain type of structure. Work on the new European technical rule for assessment and retrofitting of existing structures conducted in the frame of the CEN is currently actually very intense, with the special attention given to the heritage structures and to produce a new future Eurocode part, hopefully Eurocode 12. Many NDTs and models can be used to assess the state of conservation and physical mechanical properties for all members. However, all methods are burdened with some limitation. Although a design standard for the existing timber structure has not been prepared yet, several guidelines exist. So let me say a few words about this case study. So the case study building is situated in the city of Zagreb, and it is under protection of the Ministry of Culture. The building plot is of, as you can see, regular shape, oriented in the north-south direction. And it's situated on the flat terrain, and a total surface, it occupies a total surface area on 3,697 square meters. The roof represent, let me say, typical timber ledge pan roof constructions. The roof structure is made of 15 frames in the form of a double king bolt whose tie beams are supported by brick or bondrook parapet walls. It's been regularly maintained, and there were no significant intervention regarding the change in load-bearing capacity and structural stability. The vertical load-bearing elements consist of masonry, solid brick in the bondrook system, while the horizontal load-bearing elements consist of wooden supported beams and the roof structure. Spatial stabilization of the building was made using traverse, using wind bracing in the roof panels and struts in the frame panels. The attic space is unheated, dry and ventilated with a relative humidity of about, let's say, 60%. What was actually the final goal, the final objective? The objective was to make a complete assessment of timber roof structures, as well as to give data for design, repair, and strengthening the structure. And the final goal was to let me say, repurpose the space and make office space. Now we come to the assessment methods. And this I want to connect with the earthquake that struck the city of Zagreb, and it is, I have to say, that it's very important to have concise and comprehensive methods for a condition assessment of all the building materials. We heard yesterday about masonry, and today we talk about timber structures. A wide range of assessment methods for assessing the overall condition of existing structure is currently available. These include, as you can see, acoustic, electromagnetic, thermal, and optical methods, as well as mechanical techniques. The most common methods are visual, actually, let me say hands-on inspections, tapping, mapping of cracks, and so on. I'll talk about that a little bit later. So the first step in the assessment is to determine appropriate methods, taking into account factors of cost-benefit analysis. And the last is to incorporate the assessed data into model that will be used to calculate the remaining capacity or even reliability of such structures. You can see some of the methods on the slide, but for some of them, I'll spend the next few minutes explaining them more in the detail, so you will see in the next few slides. First of all, I want to talk about determination of duration, low duration class and moisture. So determination of low duration class and use class according to the given norms is based on a visual inspections on the roof and measurement of the amount moisture in the material by indirect method using hygrometer. The electrodes are connected over the piston to the measuring device with a cable, which is required for our electrical signal transmission. The measurement result for individual elements are given in the table, where the equilibrium humidity in the wood is defined in the mass percentages that is given as the ratio of the difference between the mass of the wet and dry wood and the mass of dry wood. So here in the table you can see the results. The next is the determination of wood class according to the norms given in this slide, and it is also based on visual inspection of the subject roof structure and measurement of density and the modulus of elasticity. In the measurement settings, the device was set to measure the speed of the signal, which is then transmitted low frequency wave of 22 kilohertz, but also to measure the maximum value of the energy of these waves. In this way, actually, the speed of signal propagation is related to the modulus of elasticity, while the alternation of the signal energy is related to the characteristic of the material. The measurement results for individual elements are given in the table, where the dynamic modulus of elasticity of wood is defined in gigapascals, given as the sum of the function represented by the ratio of the square of the transmitted wavelengths in the longitudinal direction and the detected wood density and the function represented by the maximum value that is actually been transmitted like a wave attenuation. In this way, when determining the value of the modulus elasticity, the direction of the fibers and non-linearity in the materials were also taken into account. Finally, the material density test was performed on the sample of the timber taken from the load-bearing element of the roof structures, and the investigation test have established a lower density of wood that is usual for the higher classes, which is caused by a loss of density with aging, that is the hollowing of the material over the time. Also, the expected degradation of the model of elasticity over the time has been established, and it can be assumed that the strength have changed only negligibly, which can be proven based on additional tests. On the most of the roof elements, there are visible cracks appeared as a result of moisture change and reduction process in the wood due to drying. A significant degradation, which has been caused by water leakage from the roof and by the appearance of the decay, is also visible in some of the elements. Also, some elements have been strengthened or replaced in the process of emergency restoration, but they are still considered degraded. Investigative tests done on visual inspection of the roof structure have shown that the structure is in relatively good condition without visible damage of biological origins, but with a significant number of cracks. So general structure condition and renovation suggestions. Investigative tests of the roof structures have shown that the structure is in relatively good condition, but that the replacement of degraded elements and the repair of the cracks is of great importance. Elements of which degradation appear due to water leakage and the appearance of the decay should be entirely replaced with new ones, at least C24 graded timber, and dried to the amount of moisture of wood of 15%. Elements of which degradation appeared because of wood drying and reduction are also, after the appearance of cracks, it may be repaired by using low pressure injections of an epoxy or polyurethane material. The next thing is the reinforcement, and all of the reinforcements detailed between the elements might be made by steel clamps and self-drilling screws. What else can I say? It is actually recommended to do the expansions in such a way that this layer of 50 millimeters EPS is installed below and above the tie beam, and a layer of 25 millimeter on the side, so that all the loads on the floor structures are not transferred directly to or indirectly through the tie beam. To conclude, I would like to conclude that many assessment techniques are promising methods for a quantitative description. However, there is currently lack of harmonized European standard in this field. And with the last 2 points, I would like to express my regret and as well as my desire to raise awareness about building with wood. And this especially applies in particular to the current situation in Zagreb, because Zagreb is affected by the earthquake, where the full potential of wood as a material can be exploited in the existing building. So here, that would be all from me. Thank you so much for listening, and I hope you didn't fall asleep, because a lot of interesting and instructive presentation follow below. So thank you very much.
Thank you, Nikola, for your presentation. The next one is Robert. Robert, are you here?
Yes, I'm here. Can you hear me?
Okay. Just short introduction. Robert is assistant professor from University of Chalmers. He has broad international experience in both assessment and in design of timber structures. He finished his PhD at ETH Zurich, and we are, I think, collaborating for now more than 10 years. So, and Robert is a regular team member, as I maybe didn't said yesterday in the morning, but the limit is PhD plus 7 years. So we have some professors who are advisors, but Robert is the only foreign guy here as a regular team member of our ARES group. So Robert, the floor is yours.
Yeah, thanks a lot for the nice introduction. I hope you see my presentation or my slide already. So I also summarized some things here. Yeah, I worked before in Switzerland, and now here I'm in Sweden at Chalmers University. I also I'm a bit involved in the Eurocodes, so there I also found some maybe similarities or connection points to the works there, also with Professor Rajčić, of course, and Mislav. Well, I'm working in the field or in this package on the reliability of existing timber structures, and we see that in recent years, of course, there's a lot of development in more and more interesting timber structures, modern timber structures, like these high-rise buildings we just saw as well. Maybe use of high-strength materials, so new wood products are being used in very advanced applications. And of course, maybe there are more complex structures that are not just single beams, single span beams, but they are highly interconnected, highly undetermined structures, sometimes also with very particular shapes, so that it's quite challenging to design them. And it's a question, how we can take our existing knowledge to these new structures and how to also assess the reliability of these very advanced structures. And of course, in the future, it will be a huge challenge also to maybe assess these structures. It could be that the use of these structures is changed, where maybe higher loads will be applied, or other boundary conditions change, so that we want to extend the service life of these structures or reassess them. And the challenge is how to make it in a good way, that we really take advantage of the full material properties of the structures. Maybe some thoughts on these new and existing timber structures. Of course, if we build a new timber structure, we have to design. We have to make a prediction for the future, how the structure will be, how it will behave. We have to predict or assume some loads. So it's based on a lot of assumptions and predictions, but we can then adjust or design the structure in a way that it fulfills the requirements in the most adequate way. If we have an existing structure, of course we do the assessment, and we can actually benefit from the knowledge that we have, as you already, or as you all know, and we can update, of course, the properties or the assumptions and the boundary conditions in our structure, and then we can do the verification, so that we can compare what we know of this structure with what we expect from the structure, how it should behave. I also put this a bit in a graphical sense here. So if we do the design of a truss, for example, of course we do the calculations on paper or in our files. We have to then choose a material, and we of course have all these strength classes, C24, for example, timber, where we actually have it's quite an abstract number in a way that it's a certain characteristic property of a bunch of material that has these characteristic properties, and of course with this, or based on this assumption, we then can tell the carpenter to assemble this structure together. And of course, since we don't know which board exactly is used from this bulk, we have to make some guesses and assumptions and safe estimates. And of course, the safety format comes into play, that we have the loads on one side, where we make an estimation of the loads acting on the structures, but also on the resistance side of the structure. And we have to apply these partial safety factors, of course, to keep them or to keep the distance between the load and the resistance, so to assure that the resistance is sufficiently larger compared to the load. And of course, depending on the shape of these distribution functions, so depending on the shape and the properties of our material and our resistance, we have to push both of these loads and resistance far away, so to say. And of course, we have certain basic distribution characteristics that were developed, for example, that are summarized in the JCSS, certain distribution characteristics, variabilities, coefficients of variability for the different properties or for the different wood products. But of course, these are quite old assumptions, and it should be now the task to also revise these properties and distribution characteristics, and maybe in a different structure to find different characteristics. So here you see that, of course, depending on the specific distribution type, we might end up in different partial safety factors, and if we can give a better estimation also of the properties of the distribution characteristics of our material, we can actually adjust our partial factor for the existing structures as well. So here, for example, an example of a large timber structure which was assessed in Switzerland, where you had these large beams, and of course applying now modern conservative design approaches made it very hard to or showed some problems or doubts in the reliability of the structure. But in the end, we're looking more detailed into the structure, and also considering that this structure was standing already for 40 years, it was possible to make an update of the verifications for this structure. So if, of course, we consider the very simple deterministic approaches when neglecting these distribution characteristics of the properties, it's very simple, and we can do the very quick design, but it's also very conservative. And especially for the existing structure, it's more important also to make a better differentiation of the different material characteristics of the structure. And there the updating, of course, comes into play, so that we can combine the existing knowledge with the new information. And basically that applies for all parameters in the design of the structure, such as, for example, the geometry. Here an example, Mislav might know this, roof beams. Of course, we should consider in the updating of our structure that this maybe beam is not really straight. We might maybe end up with a more complex design compared to a straight beam. But of course, we can also benefit from the updating when we compare or consider the correlation maybe between material properties. So if we assess, for example, the MOE of a structure, and we find that the MOE is slightly higher than the mean value of the assumed distribution, we can also make an estimation of the distribution function of these updated properties. So we might find that we can expect that the material properties are actually a bit better of our compared to our initial estimate. And that, of course, is then very interesting if we look at the assessment of this trust from the beginning. So depending where or when we assess the structure, we can make a much better estimation of the actual properties of the members, and we don't have to work with this bulk blurry estimation of properties, but we can kind of back trace the position of the properties of the elements and consider this, of course, in our design. So within the project, I'm currently working on an updating of the material properties of the distribution characteristics of these properties, in order to allow this updating process to consider this the distribution characteristics of the properties in a better way. And I hope that this can be applied for the existing structures, but it could also be applied to new structures where we can actually trace the elements in the structure and, of course, do comparative tests to really predict the properties of these trusses in reality. And however, also link it to the existing structures where this can be, of course, be applied. With that, I want to thank you for your attention, and I'm looking forward to a discussion later on, maybe.
Thank you, Robert, very much. It was indeed very interesting, and it's the thing we need in our project. You are the really you will be a good team member and teach us how to do all of this reliability stuff. And I hope that from our side we will have enough data for a reliability analysis of timber structures.
Yep.
I recognized the photo. So thank you for sharing this.
Yeah.
And maybe later on we can have a discussion, and maybe for now we can have just a 5-minute break till the next presentation.
Good.
Okay, the next one is at 11. David will present one case study of his. So see you at 11.